This is Jimbo. I'm from University of Southern California. This is a joint work with my colleagues, Chuanha, Mukun, and Chou. Many people became aware of such channels after spectral and meltdown attacks were reported in 2018. They affected a wide range of x86 processors by causing information leaks through timing set channels. In addition to timing set channels, there are many other types of set channels, such as power, sound, heat, EM emission. In this work, we are more concerned with power set channel. Consider this following encryption algorithm, which takes the plain text as input and generates ciphertext as output. The crypto key is stored in the device as a secret. Without set channel information, it would be hard to reverse engineer the key. However, if given set channel information, such as power consumption, it would be easier to infer the secret. Specifically, the adversary observes intermediate variables through power set channel and exploits the dependency between intermediate variables and the secret to retrieve the secret. The dependency is where the leakage comes from. What we expect to have is a sound set channel analysis, which takes the encryption algorithm as input and generates either the detected leakage or the fully verified guarantee. However, manually designing such analysis can be labor-intensive and cannot adapt to new changes. What we actually want is to automatically generate set channel analysis from data. We expect that there are some works already which you can learn or sound static analysis from data. However, it turns out that none of them could guarantee the soundness. In addition to the lack of soundness, some of the existing works even require expensive deductive reasoning. Therefore, can we automatically and efficiently learn a sound static analyzer from labeled training data? It sounds ambitious, right? Here comes our idea. We will introduce the overall framework and the learner and prover respectively. Our goal here is to develop a powerful synthesis framework, which takes the training programs and type annotations as input and generate a sound analyzer as output. Now let's demystify this powerful dinosaur framework. It consists of two parts interacting with each other. Our new idea here is really about introducing a prover to check the soundness of the learned analysis. The learner learns candidate analysis rules and feeds them back to the prover. The prover either validates analysis or rejects analysis and returns counterexamples to the learner. We firstly take a closer look at the learner. The learner also consists of two parts interacting with each other. Feature synthesis part applies SyGuS to generate recursive features, and the rule synthesis part applies decentralized learning to generate analysis rules based on those features. Now you might be wondering what the analysis rules look like. We firstly introduce training programs. There are two ASD nodes representing two intermediate variables. The input nodes are assigned with the predefined types. The UKD type represents that the input variable is secret and potentially vulnerable. The in-rand type means that the input variable is random. All the input variables will be assigned types initially. The random type means the intermediate variable is random. The type-inference rules are used to infer the type of all the intermediate variables. We firstly apply rule 1, and we can infer the type, and then we apply rule 2, we can infer type one level further. Here, we will not go into the low-level details of the rule. Instead, we focus on the learner. Our rule synthesis part makes its first attempt and generates a new tree. The red path leads to a node where two different types are grouped together. It is due to the fact that the current feature set is insufficient for distinguishing B4 and N1. Therefore, we invoke the feature synthesis part to generate a new feature with a higher information gain in order to assist the root synthesis part. After receiving the newly synthesized feature, the root synthesis part makes a second attempt and generates a new tree. We take a closer look at this new tree. Each node has been correctly classified. However, is this the analysis we want that can soundly infer the types? Actually, we are not sure either. To resolve this challenge, we introduce a prover to check the soundness of the learner. If the prover rejects the current analysis rules, it will provide counterexamples as feedback to the learner. The interaction between learner and the prover keeps iterating back and forth until starting from the ith iteration, the interaction finally terminates when all the rules are proven to be sound or it reaches a time bound. Till now, we got a general overview of the synthesis framework and the learner component, but the prover component still looks mysterious. We only know it either fully verifies the programs or generates counterexamples. Let's demystify what's inside. Inside the prover, there are two parts, knowledge base and query containment checking. The first question coming to your mind may be, what is a knowledge base? It consists of two sets of proof rules, one for propositional logic and one for distribution types. Our core idea here is to prove that the learned rule can entail the proof rules in KB. Here, I will not bore you with the details of KB. Since both KB and our learned rules are expressed in Datalog, the entailment checking can be reduced to the query containment checking, which is to check if the set of relations defined by our learned rule is also contained in the set of relations defined by KB. Here, I will use the diagram to demonstrate our idea. The black circle represents the whole universe, which consists of all the variables. The green circle represents the safe region defined by KB. The complement of the safe region is a vulnerable region. The green dashed circle represents the safe region defined by our learned rules. As long as the green dashed circle is inside the green circle, we can prove that our learned rules are sound. This may sound intuitive, but still ambiguous to you. We highly recommend you to refer our papers for more details. We developed the powerful dinosaur framework to learn a sound analyzer to avoid the human work. To evaluate its effectiveness and efficiency, we are going to answer the following three research questions, which are actually about the performance of the synthesizer framework and the performance of the learned analysis. Our benchmarks are cryptographic programs collected from public source. They are divided into training set and test set. In terms of the performance of the analysis, our learned analyzer is 266 times faster than the manually crafted analysis. In other benchmarks, the running time of our learned analysis is also much lower than the manually crafted analysis. In terms of the accuracy, we can almost achieve the same accuracy as the manually crafted analysis. In terms of the performance of the learner and the prover, the running time of each iteration is less than 1 second, which is pretty efficient. The number of rules produced in each iteration also remains modest, which is more likely to generalize. To summarize, we propose the first data-driven method for learning a sound static analyzer. We guarantee the soundness by solving a Datalog query containment checking problem, and our learned analysis can effectively detect such channel vulnerabilities. Thanks for listening to our talks, and I'm happy to take any questions.
Hello again, guys. We're waiting for your questions, I insist, okay? And I am right here in this backstage with the author of the previous presentation, Jimbo, who is absolutely eager to answer your questions. While we are waiting for them, okay, I'm going to insist in my question to the previous author that was not really answered. Well, actually, I'm going to give the floor to the public. We have a question by Martin. If you can read it and answer it, Jimbo, I will thank it.
Yeah. So there are basically two questions. The first one is like, is there anything specific to the set channel? So yes, my answer would be like there are two aspects which are closely related to set channel. The first aspect is the design of the domain-specific language. You will need to consider like how they the channel leak arise, and your design of your language should take account of that. And and also the second aspect is in the prover part, because like for different types of set channels, the inference rules may be different. And in order to prove with soundness, like we have a knowledge base, the knowledge base should be adapted to this certain type of set channels. So both the learner and the prover, they have something related to this set channel. And the second question is like, if it could be used to generate sound analysis in other domains. We have been thinking about that before. I think it is possible and promising to extend our work to develop more general sound channel analysis, like the point two analysis or other tint analysis. And the main question is like you may need to redesign your domain specific language, and also like you may tweak the prover a little bit to accommodate to your unique characteristics of this new uh, static analysis you want to develop. So yeah, that's basically what I want to say.
I am honestly I am absolutely surprised by this side channel thing because as I said in the previous presentation, I am absolutely astonished that you can identify the way that the computer is working just by listening to the noise. Well, this is what you said in the presentation: noise, temperature. I remember perfectly. In the tests that you presented in the empirical evaluation of your paper,
Mhm.
I imagine that you work with cryptographic analysis, cryptographic software. I mean, which type of channel, side channel, did you explore? I mean, was it?
Oh, I'm mainly focusing on the power set channels, which is like the power consumption is a kind of correlated with the secret. So basically, it's like if the attacker measure the power consumptions, they could be able to observe the intermediate variables. And also, then if your intermediate variable is like also dependent on the secret, then accidentally your secret will be dependent on the power consumption, so it's got exposed. In this case, is all the programs becomes leaky because the attacker can just measure power consumption and infer your key. So that's basically the what the polar set channel leakage comes from. And what I basically did is to automatically learn a static analyzer which can identify those power set channel vulnerabilities in the input programs, and to automatically detect those vulnerabilities and report them.
And if it is correlated with power consumption, it will be probably correlated with temperature. Let's say,
Yeah.
yeah, yeah, sure, go. With temperature or with noise or with other variable that probably it is also correlated with power.
Yeah, I think so. Yeah, maybe like it's possible like when the attacker try to measure the power consumption trace, there are many noisy, and like there are many factors which will influence the detection accuracy. But like we didn't really do the real device experiment. We were our work were based on a formal model, like which you call like ISW model, like abstracts the behavior of the power consumption. and how is what and the relation between the power consumption and the intermediate variables. Yeah.
No, sure, but I imagine that it should be fun to have a computer and start connecting wires to it and measure temperature and getting the real data instead of the theoretical data. I mean, theoretical data that probably it's
Yeah.
already in a file or something. Have you thought about getting your hands dirty and going to the hardware or something?
Oh, hardware.
Yeah.
Yeah, I was thinking about that before, like for the power set channel, I think it's not very related to the hardware, but for the timing set channel and cache set channel, they are closely related to the hardware, like the speculative execution, which was proposed 2 years ago, maybe many years ago. Like they were closely related to the cache behavior. I think it's more related to the hardware design. So for power set channels, like whenever the register reset a value, the power consumption is inevitable, right? I mean, so the power consumption may be related, maybe dependent on the number of the registers value and also the flips of the register. So this kind of leaking is kind of hard to patch because the power consumption anyway you have to consume it, right?
Yeah,
Yeah,
the
it's
computers need electricity and they need to work, of course.
yeah.
Let me see the name. G, exactly. G Liu is asking if your tool is publicly available, and I good at if it is prepared to be downloaded and executed.
Oh yeah, I will public my code later on because previously I just didn't organize them, and so we will public it like after conference, and all the experiments and all the benchmarks will public all of them. Yeah. I will put it in my website later on. You can check it out.
If you want to write to type in your website in the chat, you are welcome to do that, so
Oh,
they know.
okay.
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 And do you want do you plan to get rich with your research, or do you stay in academy and you do not plan to do anything with industry? What are your thoughts? What is the
Oh,
future that you envision?
okay. So I'm not sure yet, but I prefer to stay in academia at first, and like maybe 1 year or 2 years later, I will be on the job market
But
to hunt.
someone should pay for that, sure.
Yeah.
Aren't you curious about who can pay, or maybe you could make a industrial product out of it?
Yeah. Yeah. Probably. Yeah.
Well, if you can get money, you can make money. Why not? In academy, they don't pay that much in academy.
Yeah, exactly. I know that I heard about a rumor like for the SMT solver, like there used to be a group in Princeton. They developed some like completely like the CDCL the metric, and they use that patent to earn a lot of money. So which is pretty interesting. Yeah.
And should I be scared? Should I be scared that you are going to steal my credit card information from your place right? Not from your place right now because you are far away from Madrid. But
Mm-hmm.
let's imagine that you are in the next door, in the door next to mine. Will you be able to steal my credit card information or not? Should I be concerned?
Uh, I think like the credential information of yours, uh, if you have some like vulnerable channels, I may could as a if I was an attacker, I maybe exploit some of your informations like your network flows, or if I can get a device attached to your laptop, I can measure your power consumption, or I can measure the execution time of your certain kernel programs. Then
We
yeah.
go we go to the discussion room. So we invite. Okay.